So this is the equation, the basic equation. This is, can you guess it? Concentration at point x, y, z, the coordinate, is equals to Q, the emission rate, not concentration, emission rate, okay? Over 2 is a constant, pi is a constant, U is wind speed, U or U bar, and the unit is meter per second. Sigma y is the lateral dispersion, the standard deviation laterally. Remember, we talked a bit about that just now. Sigma z is the vertical standard deviation. The unit of this sigma values are meters. So sigma y can be 10 meters, sigma z can be 5 meters. They're just meters. Okay. Then exponent E, it's on your calculator, you just use the exponent on your calculator. Okay, y is the coordinate from the center line of the plume. It can be plus or minus, right? So this one can be net minus as well. Divide by y squared. Okay, divide by 2 times sigma y. I explained that just now. Exponent z is the height above the location of the point that you're interested in, not this location. But let's say you want to model here at this point. So what do you think the z for this point is? It's at the surface, right? So it should be 0. So here's 0 minus h. H is the height of the stack. Now the stack can be with the effective stack height or without the effective stack height. Like say if you don't have any details on how much it goes up before it goes downwind, then you can just use the stack height as the first estimate. So h is the height, 2 sigma z, I think you know what that is. I mentioned just now here. Plus exponent, again, this is the same thing. Notice? One is minus, one is plus. So you have all of that. If you have the coordinate x, y, z, you have q, u, sigma y, sigma z. You get it from a table. You can calculate, plug the values inside. You get c. No big deal. Very simple. It's just that it's long. You just need to put in the values. Now, remember the sigma y and sigma z. We need to, where can we get that value? This is the oldest way. It's not being used anymore, but then this is the simplest way to introduce the concept to you of how do you get the sigma y and sigma z. Now is a different way to get sigma y and sigma z. So the sigma y and sigma z is related to the stability of the atmosphere. Remember the temperature profile, where the plume goes up or down or left and right and so on. So last time they categorized the atmosphere using this Pascal's atmospheric stability classes. There are, I think, 6 classes. There's A, B, C, D, E, and I think there's an F somewhere. Where is that? There, F. Right? So A, B, C, D, E, F. I think some of you have seen this before, definitely. Right? If you studied that one, you've definitely seen this before. So you want to guess what is the atmospheric condition. We just look at the meteorology. It means we just observe the atmosphere, observe the sky, observe the weather, and use this as a guide. If let's say the winds are very low, but then the sunlight is very strong, then we can guess the atmosphere to be very unstable, A. If the wind is low, but then there's a lot of clouds in the sky, not a lot, just a bit of clouds here and there, moderate sunlight, then it's between A and B. You can choose either A or B. If it's low, but then there's more clouds in the sky, then it's B. So A is very unstable, B is, I think, moderately unstable, and C is weakly unstable. Now this is for day. Now if night, if less than 2, you don't categorize it. I think you would categorize it either as D or E, because there's not really any classification for that one. Now then we do the rest. Like say it's 2 to 3, and then the sunlight is moderate, then we say it's B, and so on. That's why it's not really a good way to classify, because it requires a person to observe the atmosphere and then to guess what is the probable atmospheric stability of at that time. But this is the simplest way for us to introduce the concept. So even though it's an old-fashioned way, but if this is the first time you're looking at how they classify themselves, I think this is a good way to get introduced to it. Okay, this is how we calculate sigma y and sigma z. So we've determined the stability category just now. So let's say we say it was B. At what distance? If it's at 1 kilometer away and it has a stability category of B, then the sigma y is 200 meters. That's all. And then using the same concept for sigma z, the most important dispersion characteristic, at 1 kilometer at B is 100 meters. And then we just plug the values inside this equation. 200, 100, 200, 100, 100, right? Very simple. Okay, so can we do this? You just need to fill up the table here.